Well, it's time. Welcome back, everyone. And congratulations on getting to week number 8. When it was week number 1, I think that was like June 15th. That feels like a pretty long time ago already compared to today. And I don't know what I just did. Oh, I closed it. Okay, week number 8 is back. So with our goal for this week, we're not covering as much new ground. Let me get that settled back there. We're going to work on section 6.2 and possibly end in section 6.3. We'll find a sensible spot to end on. If it makes more sense to begin the review a little bit early, we may do so as well. I took off the homework assignment for 6.3 and put just suggested exercises instead, since I feel like this is going to be a better last official homework assignment that will definitely complete 100% today. Well, aside from that, the final exam information went out early today, this morning. So if you haven't done so already, please make sure to schedule your final exam. Scheduling is just like it was for exams 1 through 3. Only difference is this is now a 2-hour exam. So there'll be lots of extra time to work on the problems. It's not going to be an exam where you're going to work for the entire 2 hours. A well-prepared student probably will finish it quite a bit early, but it's an entire 2 hours just to give you some thinking time, enough time to double check your work and things like that. But any questions at all, folks, to start us out about the final exam or otherwise? Okay, well, like all the other exams, it's still going to be 1 page of notes. So we'll have to kind of consolidate on the pertinent information that you'll need for this one. But I think after you look over your exam 1, exam 2, and exam 3 notes, you'll have a really good idea of how to condense it now down to 1 page of notes for the comprehensive exam. As far as it being comprehensive, we're only just finished 6.1 last class on Thursday. We're just beginning section 6.2. So the way I wrote this final exam is the last official question is really going to go up to section 5.5. And I'm going to ask one exam question with 2 parts that will involve section 6.1, 6.2, 6.3. Part A is going to be a 6.1. Part B is going to be either 6.2 or 6.3. So that last question will be fully for extra credit. And that way, if you focus on everything up to section 5.5, that is the major material that carries you over to Calculus 2. You're looking into the core parts of the exam. And I lost my train of thought. Okay, I think I'm back. There's other extra credit opportunities that we have so far. We're going to drop the lowest 5 homework assignments. And if you're behind on any homework assignment whatsoever, August 7th on Friday is going to be the cutoff date for any homework you can turn in to improve your grade. But we'll talk a little bit more about the final exam as we do our final exam review on Tuesday's class, Wednesday's class, and possibly towards the end of today's class as well, depending on how fast we go, where we end up on. And this is the review document that we're going to go over, that file in particular. Well, I think we're about ready to get started. Any last questions or comments at all, folks, before we begin? Okay, let's get started. So think of chapter 6. One major takeaway for what we're doing in chapter 6 is not just about applications to the integral, but for us, it's more a big opportunity for us to practice integration just a little bit further beyond what we did in chapter 5. We did lots of work on differentiation. Integration feels like it doesn't have its fair amount of time, but that's where Calculus 2 picks up. More problems, more applications. So we looked into an application on the area of the integral, and now we're extending this over to volumes. And bear with me a moment, I forgot to do one thing and load in the pens on this thing. Kind of tedious to do this every single time you open this workstation, but it is what it is. Give me one moment. Doesn't hurt to have highlighters. Let's get these going as well. Okay, and that's the wrong button. Let me try again. Okay, I think we can get started. So this is our next application. We're extending from areas now into volumes, areas between curves to volumes. And this is the kind of object we'd like to say for our visual here to find the area of. Looks like it's some kind of bone. Maybe it was dug up on some archaeological site. Who knows what's going on? But if we have something like this and we'd like to find its exact volume, there's lots of ways to do it. Maybe you could just drop it into a bucket of water and find out how much water gets displaced. But maybe it's something you wouldn't want to ever submerge. If that's the case, you happen to know the exact structure of this to the point where you know all of the cross-sectional areas, then we have another alternative way to find the volume. So if we can't dunk this underwater to find out the volume of water displaced, here's our alternate approach. So S is the solid. It's constrained between A and B on just the horizontal x-axis. So that's a solid that lies between those regions. And if the cross-sectional area S, that's this area we're talking about when we say it, with in the plane P of X through X perpendicular to the x-axis. So just this plane right here, this slide, that like a movie goes from A all the way over to B. Imagine this region here changes, the area changes as well for that cross-sectional slide. If we use the same approach that we took to define the definite integral, same approach that we took to define area between curves, we could partition this axis from A to B with n subintervals and approximate the volume of every one of these cross-sectional slides. And this is what it would look like. We would take the area, delta x, would be the thickness of each one of those slides. So now that's a true volume you'd be looking into altogether. Take the limit of the number of the slides as n goes off to infinity, and this would be the definition for the exact volume of this particular object S. But once we get to this part right here, this is a limit of Riemann sums. And this is really the second punchline for the application to the integral. In the sciences, not just volumes, but really anything that can come up, work, forces, and so on, if you can pose the problem as a limit of Riemann sums, sometimes this is a point of celebration because a limit of Riemann sums can be written in this way. If A of X happens to be continuous, then we can celebrate even further because if the area is a continuous function, as X varies, we can just use the fundamental theorem of calculus to evaluate the limit, solving the definite integral, thereby giving us the volume all in one shot. So if we assume continuity, we just use fundamental theorem of calculus. Use the fundamental theorem of calculus. So that's the idea. If we integrate area in the right sense, where it's a cross-sectional area of S of X, then we're going to get the volume of the entire structure. Any questions about this setup so far? Okay. One extra thought you might connect with this compared to something that we did way back in chapter 3 is, I believe in section probably 3.9 maybe, we took a derivative of something with respect to r, say pi r squared. That was the area of a circle, a two-dimensional object, and we got to 2 pi r. That's the perimeter or the circumference formula. So if we differentiate it, something that's area, we go one dimension lower and we have a perimeter. And this one's going backwards in a certain sense. If we had the area and we're integrating, sure, it's a definite integral, but first step in the fundamental theorem of calculus is to take the antiderivative, taking the antiderivative of the cross-sectional area in the definite integral here, now going backwards in a certain sense, is giving us volumes instead. So it's as if we're going from something that's dimension 2, integrate it, and we're working in something in dimensions 3. And so that's a great analogy to think about in terms of both differentiation and integration. We're just changing the dimension of the physical thing we're analyzing. So now we need to analyze this, compute some areas to get us started. And one thing that's really tricky about these notes in section 6.2 and section 6.3 is the visualization aspect. Sometimes visualizing these things is not easy at all. For example, on this one, we're going to find the volume obtained by rotating the region here in blue across the x-axis. Now we have a three-dimensional structure as a true volume that we can measure or compute. And these are not always easy to draw. So we'll be practicing doing these by hand and the problems beyond this one. But I'm no artist either, so if you struggle drawing these kinds of things, no worries. We'll show some good strategies for getting through the artistic aspect of it. But first, this is the visualization taken from a different textbook to help us show how to put all the ideas together. So first, we have three curves. One with actual curvature, y equals square root of x is this curve in blue. Then y equals 0 is just the horizontal axis, bounding this way from 0 to 4. X equals 4 is just the vertical line segment. And it gives us a region in blue, but that's just an area. So we're doing a rotation. We're rotating about the x-axis. And if we do that, here's the thing that has now a true volume. So imagine this as a movie. As it rotates about the x-axis, it sweeps out a solid structure, and we want this volume. Who knows what this is going to be used for? Maybe something industrial. Who can really say? This is just a random math problem. But you can imagine this is really practical. If this is something done in industry, and you have to manufacture maybe 1,000 of these or 1,000,000 of these, you might want to know their volume. And even if you're a home user trying to build this to replace some kind of part in your refrigerator, who knows, you might want to know how much ink you're going to need in your 3D printer to manufacture something like this. Using calculus, we can get the dead-on exact answer of that volume. So first, in the process, here's the formula. The volume is going to be the integral from a to b of a of x dx. But when we write down that formula, the a of x has a very specific role. It's this kind of area where you have a cross section as you sweep through your three-dimensional structure. You have to find that area function a of x. In our current problem, to get a of x, we have a pretty decent visual of it already on this down below here. Imagine x goes from all the way down to 0, where it's just a point, all the way up to 4, where it's a circle with radius 4. You can get the area of the cross section of this three-dimensional structure at really any point. Here, just use the area for the circle. As x goes all the way to the other end, the area is 0 because now it's just a point. It has no area whatsoever. But a of x varies as x varies, and so we need a bona fide formula for a of x itself. The fundamental thing about these problems are we're doing a lot of problems where we're rotating either about the x-axis or the y-axis. And as you do that, circles just start to emerge. So we can just use the area formula for the circle to find a of x. So that's the setup to the problem so far. Any questions before we start writing down the formulas? Okay, so for the formula, let's go with this color here. A of x is going to be the area of the cross section as we go from 0 to 4. But now that we observe it's just a circle, we can say it's equal to pi times the radius squared. But the radius is also changing, so we can call it r of x to the power 2. And that means we need to regress a little bit further. To get the area, we need to find the radius. So this is radius now. But we're getting there. New function we need to pick up is r of x. As x goes from 0 to 4, and we rotate the whole structure about the x-axis, we get to these pictures. We'll hand draw some of these the best we can, but that's just going to be pi times a radius, or excuse me, I'm writing down the area formula. The radius formula is just going to be this length from here to here. Sometimes the radius is 0, sometimes the radius is 4, but x came from that curve. The height of that curve is giving us the radius all at once. And so once we have this, we have the radius as well. The radius is just square root x. So now, once we put all of that together, we can say the area at x is just going to be pi times the square root of x to the power 2. That means it's just going to be pi times x altogether. So that gives us the area of the circle at any point x as it ranges from 0 to 4. Putting all of that back together, all we had to do is integrate the cross-sectional area from A to B. So now that formula for volume is ready to go. We're just going to substitute everything back inside of there. So this is the point at which we get to practice integration. The problems will get trickier and trickier bit by bit as we go through the notes to give us more and more practice. But any questions before we go to find this volume? Okay, well, putting this together, we can now say, by the work above, we have volume. First, we have to give the limits of integration. We're rotating about the x-axis. We're letting x vary from 0 to 4. And that's where the limits of integration will come from on this kind of problem. So if we go from 0 to 4, the thing we're integrating is the area function, a of x. It devolved down to just pi times x with respect to x. And that's a really fast definite integral for us to solve. Integrating this is just going to give us, for an antiderivative, pi times x is going to go up to power 2. We'll divide pi by 2 to counteract that new exponent. Then evaluate x squared from 0 to 4. So this line down below, that's the fundamental theorem of calculus, part 2, the evaluation theorem. The antiderivative is x squared, also divided by 2, but I left that factored out. All we do now is just evaluate x squared from 4 to 0. So this becomes pi over 2, 4 squared minus 0 squared. And so we're just about there. This is pi over 2 times 4 squared, which is 16. And so that'll tell us the total volume is 8 pi. We don't have a unit on this. You could say units cubed if you like, but that's not necessary. Just a reminder, it's a volume. And that's the entire process for finding volumes under these kind of curves. But we did it, folks. That's our first volume computation. It's kind of interesting that we can extend from area under a curve to areas between curves. Now extended further, we can recompute volumes. Volumes get trickier and trickier the more that gets involved with it. So that's also what Calculus 3 is all about, finding volumes in different kinds of scenarios. But for these kinds of scenarios where we rotate structures about the x-axis or y-axis, this is a fast way to get volumes without delving all the way into Calculus 3 to make it happen. Well, we'll practice more of these in these notes, see if we have more time for section 6.3. But any questions at all getting through the first one? Okay, let's give the next one a try. The thing to keep in mind that really all of the work in these kind of problems is really just to get down to here. Once you have the definite integral, then you're sort of home free. So all the real fighting is figuring out what the area is, finding out what the bounds are for integration, finding out what the radius is, And these diagrams tend to be really, really helpful. Oftentimes, if you draw just this one and imagine this red segment here rotating around, giving you a circle, that's enough to get started, even if you don't want to visualize the entire three-dimensional object. So with that in mind, here's our next one we're going to compute on. We want to find the volume of the solid obtained by rotating the region bounded by those two curves about the specified line. This one's about the x-axis once again. For this one, we want to sketch the region, the solid as best we can, and a typical cross-section. The typical cross-section would be much like that disk that we saw here. So lots goes into this one. First thing is we have no information on what the bounds should even be for integration. So that might be a good starting point for us. If we're going to do any curve sketching, we want to know the domain for which we're going to sketch that curve. So for this one, take y equals x squared, y equals x power 1/3, or cube root, and just equate both of those. So once we equate those, we can now get values that we can get on x for which the y coordinates are both equal. Solving this one's not too bad. We would just want to raise both sides to the power 3 to remove that exponent there. So on the left, it's x squared cubed. On the right, it's cube root of x, or x power 1/3, raised to power 3. Decent algebra review on its own right. This gives us x power 6 equals just x. Then solving this one, if you were going through the methodical steps, probably the next thing to do is subtract x from both sides. We have x power 6 minus x set to 0. Once we get here, our next step is just to factor. That leaves behind x power 5 minus 1 set to 0. And from here, we can read off the solutions. One solution is, let's write here, this implies x is 0 will bounds for this equation. And because we're only looking for real valued solutions, the only solution here is 1. And those are the two values that are going to solve this equation here. In hindsight, you might have already knew that. So if you know these values and you can just predict that, it wouldn't be too bad to skip down to this step. But sometimes it's not straightforward what exactly they should be. So these would be the methodical steps that would work in either one of these kind of situations. So we're going from 0 to 1, rotating the whole thing about the x-axis. And now this is a decent point at which we can start sketching the curve. Any questions with the algebra review side here, getting the bounds? Okay, let's now sketch the region that's going to be rotated about the x-axis specifically. It looks like everything is happening on quadrant 1, but it'll also involve quadrant 4 if we're rotating about the x-axis. So this is about what you'd want to plot over. We're going from 0 to 1, so that could be our 1. That seems to match on this unit. When x is 1, the y values on both curves is also 1. So that'll be a decent scale. When x is 0, we know that they also match because we solved it. When x is 0, the y coordinates are both 0 as well. So they both start here. They both end here when we sketch the curves. And x squared is the more straightforward one to sketch. It's just a parabola going from 0 to 1. We know it has this kind of shape. The parabola is going to be concave upwards, in other words. And the cube root, much like the square root, fourth root, fifth root, and so on, that one is concave down, so it'll have this curve. Now maybe this is a good point to start color coding these to show them showing up on the plot. So here's y equals x squared. Here's y equals x power 1/3. So we have kind of an interesting shape. It's not sketched perfectly, but we don't have to be a computer. We're just trying to get a nice hand-drawn sketch so we can see how to put the integral together on the next steps. And now next thing that happens is the whole thing is rotated now about the x-axis. When that happens, we have a kind of a weird geometric object. It's almost impossible to come up with a good use case for this, but again, maybe it's used for something industrial. Who knows? Maybe it's building the next hydrogen fusion reactor or something that has weird metal parts in it for sure. If we rotate this entirely about the x-axis, we'll have one piece that ends up here. I won't require you to sketch the whole entire solid. Let's skip it on this one so we don't get too sidetracked on just the three-dimensional art itself. The cross-section is going to be the major thing that's going to help us sketch the actual, or put together the actual definite integral. So this whole thing rotates around. And now let's put in the typical cross-section. So when we're thinking about the typical cross-section, we're imagining a picture kind of like this one. We have some random three-dimensional object, and we're putting down a plane perpendicular to the x-axis that sweeps from one bound to the other, giving us the area, function a of x. Or much like in this diagram here, this would be the cross-sectional piece. For our curve down below, we have a three-dimensional solid. Again, not easy to sketch this. Imagine another shadow piece here, but the whole thing is rotated around. And I'm just going to imagine a value x between 0 and 1, maybe say right around here, anywhere that's easy to plot. You want to pick either 0 or 1. You want to find a value somewhere in the middle. So if this is your value x, as you move upwards, you get this piece going from here to here. This whole piece right here is going to rotate about the x-axis, following the rotation. And when it rotates, it'll give us this other piece down below. So this time we don't exactly have a circle. We had a perfect circle here when we rotated the red curve, which came from this portion right here. But on this one, this is analogous to the red curve we saw there. When we rotate this thing, we get a piece that comes down about like that, around, down about like that. And we get kind of a washer, or an annulus, you could call it. So this is the cross-sectional piece that we're going to be dealing with. If we can find the area of that cross-section, and it changes as x moves from the left to the right as well, if we can find the area function for that, we're home free. We'll know exactly what the volume is for this entire thing as we rotate about the x-axis. So that's the sketch so far. Lots goes into preparing just to write down this integral. And it's kind of a tricky one because our area is just this band right here. If you like, you can revisualize this. Imagine you're looking at the x-axis, your eye level is looking down in like that. If that's the case, where the red dot is, you could just put a solid dot there. There's going to be an inner circle. And for that inner circle, let's use this suggestive color instead. The inner circle you see here came from this one. Its radius depended on the curve that's in green. That's the y equals x squared curve. And again, imagine these are perfect circles. Don't have a good hand for circles today. As you look down on this washer from the x-axis, you'll also have this outer circle that defines the washer. And we want the area shaded in orange here of this particular object. So here's our cross section. Viewed either sort of in 3D to the best of my ability to draw it, or here as a two-dimensional object. If we can find the area of this cross section, then we're on our way. And it's not too bad. The area is going to be area of outer circle minus the area of inner circle. So if we took just the area of the outer circle, we're talking about the one in blue here. And that blue curve right here came from this segment, y equals x power 1/3. If we took the area of just that, our area is way too much. We subtract off the area of this inner circle right here. And now we're just looking at the area between. So that's going to be our strategy. Look at area of outer circle, which depends on, wrong color here, that curve in blue, minus the area of the inner circle, depending on that curve in green. They're both circles, so if we can get their radiuses, or I guess radii is the better way to say that, we're home free. We'll just use the area formula for the circle twice. So first, let's look at this radius. We're going from here to here. I'll call that R1, since we have two radii this time. R1 of x is just going to be, when you go from x all the way up to this height. This height here determines the radius at any value x whatsoever. It's just x to the power 1/3. Then, whether we're looking at this diagram and trying to find this radius from here to here, or visualize this way on the two-dimensional diagram, this would be R2 now for second radius. And R2 is when you go from the center, right on the x-axis, up to this height. This height also varies with x, but it's always equal to exactly x squared, no matter where x is. So now R2 is x squared. And from here on out, we can put these all together. Area of x is going to be pi. Take pi, multiply it by the outer radius, R1 squared. That's just going to be x power 1/3 raised to power 2. So just pi radius squared for the whole blue circle as an area, minus pi multiplied by a different radius squared. That's going to be x power 2 squared. So here's x power 2 to the power 2. When we subtract off this area, that's now blowing a hole out right here. So now it actually looks like a real legitimate washer. The dimension of this washer varies along with x. And that's going to be its area at every value for x, as x goes from 0 to 1. So we can simplify this a little bit more. We're going to integrate it, so it's well worth our time. First thing we can do is just factor out pi. Then x power 1/3 squared just gives us x to the power 2/3. Minus, skip pi, we factored it out. This is now x power 4. And that's our area formula. With that, finally, we're ready to integrate something. This one had quite a lot of setup just to get started, mainly because now we're looking at an annulus, or a washer is the other way to name this object. I think I like calling it a washer better. But once you have that area, this problem is really no different from just taking the square root of x like we saw here. Here it was just one curve, so we just found the area of this circle instead, and we were able to just go right from there. So we're ready to finalize this problem. In the end, we can say, let's put a little fancy therefore symbol to say, by all this work above, the total volume of this region, once we've rotated about the x-axis, will be a definite integral going from 0 to 1. That 0 and 1 were these values from here to here, coming from when we solved for the limits of integration on our very first step. We're integrating the area function, a of x, dx. So that means integrate from 0 to 1, pi times x to the power 2/3 minus x power 4 dx. Haven't really achieved much to this step other than just substitute in the area function. But we really are nearly there. We can say that this is pi times, take the antiderivative there. If it's to the power 2/3, we add 3/3 to that, divide by the result, which is 5/2, giving us hang on, I almost got there. Let me backtrack. This is a good review practice already. If it's 2/3 there, you add 3/3 to it, and you do it right there. So now it's 5/3. Don't know why my brain skipped that step. And then when you get those 5/3, divide by it, multiply by its reciprocal, 3/5. So that's our first step. First antiderivative, and just do it all over again. New power on x is 5. Divide by that 5. So 1/5. And now evaluate the whole thing from 0 to 1. That's it. That's the volume. We just need to get a numerical value down. Any questions on getting to the antiderivative? Okay, well, here's our last steps to conclude this problem. I'll leave pi factored out. We're going to throw 1 in to this antiderivative from the upper limit, but 1 to a power 5/3 is still just 1, so that becomes 3/5. Same story here, minus 1/5. And when we throw in the lower limit 0, we're just putting 0 in for x. That's going to subtract off 0, so no change there. I'll put minus 0 to just say we didn't forget that step, but nothing happens. This whole thing gets wiped out. So it's just 3/5 minus 1/5. That means it's pi times 2/5 altogether, for a total volume of 2 pi over 5 units cubed. I'll just leave it as that direct answer, no units, 2 pi over 5. So if you ever have to manufacture this kind of thing, who knows what it's for? Maybe it's some kind of fruit bowl. Doesn't look like it would hold liquid well because that's 1 point right there. The 3D printer is probably not going to give you anything that holds on that spot. But this is the amount of volume you can expect, 2 pi over 5. Well, that's 2 problems down. Example 1 is the kind of more routine problem that already had the sketch for us. Example 2 got a little bit more busy because we had to deal with a washer type shape this time, not just a circle. But these kind of steps defeat the problem every single time. If a washer comes up, just look for the 2 radii that you're going to work with. And it's always this formula in this kind of way. We'll look into one more scenario before we take a look into the next section notes, section 6.3. But any last thoughts or comments before we try another version? Okay, well, here's our next problem to tackle. One thing to note is you might have noticed that we've been rotating about the x-axis for quite a bit on these. And that's what section 6.2, using cross-sectional areas that we integrate, is really meant for. We want to rotate across the x-axis if we're going to be using this kind of method. That makes the next part a little bit more concerning on example 3, because this time we're rotating about the y-axis. So some words of advice, some comments to get us started on this one might be the following. Section 6.2 requires a rotation about the x-axis for a definite integral from a to b of a to the x dx. So if we're rotating about the y-axis, when this comes up, it means we're going to pose the problem a little bit differently. We're going to write, let me put a little bit of space here and put v equals, just to remind us, this is all for volumes. That's the only reason we're doing this, to compute the volume. So let me say for volume. So this time we'll write volume equals an integral from a to b of a of y dy. So that's the major idea this time. If you're changing the axis you're rotating, but you're still using the section 6.2 method because that's the only method we discussed yet for volumes, then we need to change our perspective entirely. We're going to let y vary between bounds from a to b and do a dy integral, integrating about the y-axis this time. And we've seen this before. Let's take a look into some preview material just for some inspiration on how this goes. In section 6.1, we were doing areas between curves. We had a Riemann sum, express it as a definite integral. And the prototypical problem we looked at was this one. To find this shaded area here, we just take the upper curve, the root x plus 2, minus the lower curve, 1 over x plus 1, integrate as x goes from 0 to 2. So that's solved the problem for us. But that's not always the most convenient way to pose certain problems. And this one was a much different kind of problem. This time it was x equals a function of y for one curve, x equals a different function for y for another curve. We want to do this area. It's now a dy integral, much like we're looking at a dy integral here, because we're rotating just about the wrong axis. And it's an important technique to sometimes take. Sometimes one axis is way more convenient, or really the only tractable way to do the problem exactly. So if it's a dy problem, that means we imagine y going from one bound to another. That's why we're going from 0 to 1. I guess it's 0 to 1 either way you look at it. But if this was from 2, we would have been going from 0 to 2. And then, if you turn your head a little bit to the right, we can see that this is the upper curve this time, and that's the lower curve, y equals x cubed. So we went y squared minus y cubed, and now we want to do the same kind of idea in example 3. These are good problems to practice. They're tricky, changing our perspective in this kind of way. That's something that happens a lot, not just in the calculus class, but in any applied setting as well. We'll see plenty of this kind of stuff in a calculus 2 setting as well. So this is all kind of warm up for this new idea. So interchanging the role of what is x, what is y. One way to do that is, let's start writing down just an ordinary x and y axis. I'm not completely sure what role everything is going to fall in, so I'll just give equal weight to all the coordinates this time. So we have bounds y equals 0. That's just this entire axis, the x-axis itself. We have another bound, x equals e, and let's place that one. That's not a bad one to start. Here's 1. Let me space that out a little bit more. Here's 1, here's 2. E, I guess that's not quite there. Let me fix my tick marks. 1, 2, 3 is about as far as you want to go. E is about 2.7 and some change. I don't know how far I have to go up or down, so I'm just going to put a temporary dashed line where E would be. So we'll refine that a little bit further. Here's the E value. So that's one curve down, that's another curve down. And now we have x equals e to the power y. So if we're looking into e power y, one way to think about plotting that is you could solve this for the y variable. That's not always very easily done. Or we can just imagine, once again, the roles of x and y have been completely swapped. This is the positive y-axis. This is the negative y-axis. And if we plot an exponential function, x equals e to the y, it will look about like that. Doing a dashed line because, once again, I don't know how far I need to plot. We're trying to sketch the region where the area is finite, enclosed by whatever curves they give us. But now, looks like there's a region right there where the red dot lands. It's bounded by the x-axis, y equals 0, vertical line, x equals e, and x equals e to the y, this curve right here. That's kind of an awkward way to plot, so if you like, there's no harm really taking x equals e to the y. Take the natural log of both sides, and you have natural log x equals just y, because natural log e power y cancels to just y itself. If you look at that really closely, yeah, that's just natural log x that you're plotting as well. So lots of different ways to visualize this kind of problem. Let's start enclosing these curves. We have a line going this way. me try and make that a little bit better of a line. So this is x equals e to the power y. We have another line segment going this way. We can erase the dots and put a definite line. This is x equals e. We can erase these now as well. We don't need quite so much of that. We can just focus on this section right here. Looks like a shark fin or something along those lines. This whole thing is now about to be rotated about the y-axis itself. Let's maybe get a little bit more information. Let's get the height right here. If you plug e inside of this, if x is e, you'd be plugging inside here, and natural log of e is just a 1. So this curve has height 1 altogether. Then it rotates this way. Here's the y-axis rotation. When that happens, we get this whole piece sweeping out an entire three-dimensional solid. Again, it looks like some weird kind of band of some kind, maybe a ring of some kind that we're looking into. Let me draw another piece that looks about like this. So if we rotate this across, this is going to be its reflection across the y-axis. And it doesn't hurt to make that a little bit more solid. Here's a reflection. And now we want to sketch the typical cross-section. If you're really good at sketching three-dimensional objects, you can sketch the entire solid. But once again, I think that requires practically an art class. You have to be really good at shading to show this entire volume, much like we were showing the volume on this one with some good shading to help out. So let's now put down the cross-section. Idea for this one is we're doing a dy integral, so we need bounds for where y goes. Let's put that down. 0 is going to go, y is going to go from 0 all the way up to 1. So we have 0 is less than or equals to y, less than or equals to 1 altogether. We want to pick any arbitrary value, excuse me, between 0 and 1, just so that we can have a really quick sketch for what we're about to plot. Let me do this one in green. I'll do one about here, closer to the top. Here's one arbitrary value y. Now we're doing areas by a cross-section, so we're imagining a plane perpendicular now to the y-axis that moves up. Right around here starts intersecting this solid, which is, again, a strange-looking wedding ring of some kind. Looks like it'd be painful to wear. Once it gets up to this height, the cross-section looks like this. We move to the right. Here's where we have an actual area segment. That segment there gets duplicated, reflected off to the left. The whole thing is now really just a washer, like we saw in the prior problem. Here's one end of it going this way. And here's the other end of it. These diagrams get kind of busy as you sketch them all together. So it's good to kind of go in stages, see how the diagram is built. And the whole purpose for getting this diagram is this washer in green, we could revisualize it in 2 dimensions if we'd like, but that is the thing we need the area for. So this is the cross section. Here's a typical cross section as y varies amongst its bounds from 0 to 1. Shown in a different way, here's it in 2 dimensions. We have a solid dot representing this point in the 3-dimensional structure. Then there's 2 circles, just like from prior example 2. There's an inner circle. Let me try a little bit harder on that circle. That's worse. All right, last try. We'll just stick with this one. Here's the inner circle. That's when we're at this point here. The outer circle when we're way out here. There are 2 radiuses for us to focus on, and we get it just from those values there. One radius, when we go from here to just here, let's call that R1 of x. We have a function for that already, R1, excuse me, not of X. Let's backtrack on that. One thing to remember is that when you're rotating about the y-axis and you're interchanging the roles of x's and y's, the integral is now dy, and now all of our functions are functions of y. We should call this r1 of y as a variable. R1 of y is this, e to the power y. So the roles of x and y's have completely swapped. We can't call this r of x any longer, like it's tempting to do so in all the other problems. So that's the radius going from just here to here, the inner radius. The larger radius is actually constant. No matter how high y goes from 0 to 1, it always has a higher radius exactly at e. So going this way, let's call this r2 of x, excuse me, r2 of y. That's something to get used to sometimes. R2 of y is just e itself. So now that we have both the radii, we can put the area function together, and after that, it's just a short step to integrate. Well, we're mostly there. The major struggle, the major challenge, like we mentioned before, is just to get to the integral. But once we have the radii, we can very quickly find the area of this washer that we see visualized here. So this is the cross section as well. Any questions before we write down that area? Okay, so here's our area function finally. Area, which now depends on the variable y, is going to be take the outer circle radius, like we did on example 2. That's just going to be pi times a radius squared, but that'll be r2. So pi times r2 of y. Then subtract the other area, also a circle, the one with the inner radius. That's going to be pi times a radius squared, but it's r1 of y. Like before, we can just factor out pi for convenience. We have pi times r2 squared is going to be taking this right here and squaring it. So this will just be nothing but e to the power, I guess we can drop the color coding and just call this e squared. So once we've finalized that, r1 squared is taking e power y and squaring that. So this will be minus e to the power y squared. Better to write that as e to the power 2y for our purposes. So area, which varies about y for the cross section, is pi times e squared minus e to the power 2y. Now we've got the area. We know where we're integrating. The bounds on y are from 0 to 1. And this is where the problem is about done. We can say once and for all, therefore, the volume is the definite integral as we go from 0 to 1. Those are the bounds on y. Take the function a at y. And we must now also say dy. This is no longer a dx integral. And it really matters because if we did say dx, the answer would be that. Just the length of the interval, 1 times a of y. But that's not a number at all. That's not going to give us a volume. So we really have to say dy to say what is the variable of integration with respect to. So now we've abstracted away from the three-dimensional object now to just a definite integral. It now becomes all about solving this. Let's substitute in some more, the actual area itself. We're integrating from 0 to 1. Pi times the group e squared minus e to the power 2y dy. And it's not a bad integral to work with, except there's one little tricky element that goes along with this one, and that's right here. That is a function composition. Whenever a function composition comes up, if we are differentiating, it requires the chain rule. So although we're not differentiating, let's review that. d dy of e to the 2y would be e to the power 2y times the derivative of 2y, which is 2. So when function compositions come up, we need to be a little bit more careful if we're taking an antiderivative. The antiderivative of that, e to the 2y dy, that's really our section 5.5, u substitution, shows us how to undo the chain rule whenever this kind of thing comes up. Sometimes, however, you might be able to make a pretty good prediction. If the derivative of e to the power 2y just involves multiplying by 2, the function e to the power 2y, a decent prediction is antiderivative of e to the power 2y should be e to the power 2y, I'll say plus a constant because it's an indefinite integral, the way I'm writing it as a formula here. But the derivative of e to the 2y is not that, it's twice that, so we just counteract by putting in a 1/2. So this is a pretty decent way to solve the problem. In fact, in Calculus 2, this is the way some of these u substitutions just get solved. If it's just a matter of being off by a constant, you imagine what is the constant we need for the derivative of the function to equal the integrand, and we just throw in that constant, sidestepping u substitution. We can't always do that, so we do plenty of u substitution in the next course. That's a decent visual. So if you decide to do that in a homework setting or an exam setting, you would never lose points for that. So we know the antiderivative of e to the power 2y. Any questions about it at the moment? Okay, and maybe another thought. U substitution is a pretty impressive technique, but it's also tricky. A lot goes into that. And because we're about to review for the final exam, really starting tomorrow, let's take another close look at this to see the alternate way to solve it, just for the sake of review, since once again, we're about there anyways. Hang on, Microsoft Word is arguing with me. So I'm going to call this, just to say, a fast review. Section 5.5, fast review. Here's another way to solve the whole problem. Find the antiderivative, so indefinite integral. Let's just call it e power 2x dx, and solve it as if it's its own problem. We know we can switch to variable y, and the answer would look like that if we wrote it that way. So once again, there's a composition here. If it's differentiation, chain rules involved. If it's anti-differentiation, we reverse the chain rule, and now we're going to use u substitution. So in u substitution, what we're looking for is the inner function. The inner function, the composition is that 2x that we see here. So that's not a guarantee u substitution always works this way, but this is the starting spot. Best place to start for u is let it be the inner function 2x. Now, once we've chosen a u to use in u substitution, we take its differential. Differential means there's going to be a du on one side. Let me keep the color coding the same as last time. There'll be a du on one side. There will be a dx on the other side. And between those things and the equal sign here, we take the derivative of whatever the function is. It's 2x, so the derivative is 2. So that's now the differential. We look into what we have in the integrand. Dx is there, so that's good, but 2 is missing. If 2 is missing, we can just multiply by 2 over 2. That forces a 2 inside. Our author often just divides out that constant 2. So I only went that route in section 5.5. So I'm going to rewrite this as 1/2 du equals dx. So with all of that in play, we can now go back to the original integral here and make all the substitutions. We'll write equality, give it some space, and then the integral sign. This is now e to the power u. 2x has been substituted in for u, and even more, dx is also changed. Dx is now 1/2 du. We can move the 1/2 way outside with the constant multiple rule. Du goes here. And that's the full entire substitution. So now when we go to take the antiderivative, we're just getting 1/2 times e to the power u. Add the constant. We still have one more step because we must undo our substitution. So that u has to be unpacked and rewritten as 1/2 e to the power 2x. The expression we defined u to be in the first place, plus a constant. So that's the full tour, start to finish, using u substitution. Like we mentioned before, sometimes u substitution, it's a requirement. Sometimes these integrals are so tangled up, you can't do it in your head like you see right here. But because we do these so often in Calculus 2, if you saw e to the power 2y, and just notice it comes out right if you throw 1/2 in front, that's a great way to integrate these ones when that happens. I guess the short story is, if you can do it in your head, you're welcome to do so, and it's encouraged in the next class, because that's a lost step to do every single time when you don't have to. Well, any questions at all, folks, with the fast review before we go back to the volumes and finish this off? Okay, well, either way we look at it, antiderivative of e to the 2y, it's available for us, whether we write it in terms of x or in terms of y. We'll keep it in terms of y to match the problem that we're solving here, and say that the volume is now equal to pi times, and we take an antiderivative. E squared is just a constant, so we just multiply that by the variable, not x. The variable in the problem is y, if we say dy here. So it's e squared times y minus, antiderivative here is 1/2 e to the power 2y, and all of that's evaluated from 0 to 1. Gotta like the zeros, they kind of make things nice, but watch out for e to the power 0, that becomes a 1, doesn't wipe it out. So we're ready for the fundamental theorem of calculus. We've got the antiderivative in play, so we can now just say the whole answer is pi times the result of, and let me use brackets this time. Plug 1 inside the function here, we'll get e squared times 1 minus 1/2 e squared. Altogether, e to the power 2 times 1. Then go minus, plug 0 in, and this is just e squared times 0. Minus 1/2 e to the power of 2 times 0, or just a 0 for short. We've got to simplify this down, but shouldn't take too many more steps. Altogether, this is pi times the result of, this is just e squared minus a half of e squared, really. Oh, it doesn't hurt to write that in the next step, just to clean it up. E squared minus 1/2 e squared. Then that's 0 minus a negative 1/2 e squared, so just plus 1/2 e squared. Excuse me, not e squared, plus 1/2 e to the power of 0, which is 1. So that's our e power 0, so we get just plus a half altogether with the double negation. So now the result is pi times, this is 2 over 2 times e squared minus a half e squared for a half e squared plus a half. That's a completely fine answer just as it stands. I think it looks slightly more simplified if you factor out a half. Rewrite this as pi over 2 times e squared plus 1. So kind of a strange listing of constants. It's definitely a positive quantity, so if it was negative, we would know something's wrong. Maybe we subtracted the radiuses incorrectly. But it says if we take this little weird shark fin looking structure, rotate it about the y-axis, the result here is now the total volume altogether. So that's dealing with the y-axis. It's tricky because mainly of this part right here, interchanging the roles of x's and y's entirely can get a little bit convoluted. If we track everything down, keep things in terms of dy, limits of y, and functions of y, we had to call that r1 of y specifically. Really, it's no big deal. It's just kind of like what we did in section 6.1, changing the roles of x's and y's. Well, you got it, folks. To me, the more challenging thing is also just actually drawing the three-dimensional structure. So your imagination is a big part of these kind of problems. Any last questions or thoughts before we take a look into the next section, 6.3? Okay, let's close this out. And this is a good time to celebrate because we're going to consider 6.2 to be the last full official section for this entire course. So for Calculus 1, this is the last homework assignment. This one is due on August 5th, which takes us way out to Wednesday. I decided to drop more homework assignments than what the syllabus said. The syllabus said the lowest two. But I felt for the fact that this is an 8-week fast-paced course, and we solved a section just today on the final week, dropping the lowest 5 did make sense. So if you don't quite get to this one, it's not going to hurt you in the end. That's one of the reasons I bumped this up to 5. I'd say the major homeworks to get through would definitely be up to section 5.5 and 6.1 would be the major ones. That'll boost your score in a nice way. And now for section 6.3, volumes by cylindrical shells, here's the major idea between both these sections. 6.2 is a great section. The methods used there for rotations about the x-axis. So if you're rotating about the x-axis, that's a great section. If it's rotated about the y-axis, you might be able to change the roles of x's and y's and still solve the problem. Or there's another method that's sometimes a little bit cleaner, depending on the region that you're integrating. So this method is better suited for rotations about y-axis. So if you rotate something about the y-axis, this section is much better suited for that particular rotation. So let's screenshot this, drop it into our notes just as a handy reminder for when to use which method. And here's our last section that we'll take a look into. This section does not have an official homework problem associated with it. And like we mentioned earlier, that there's going to be one problem that's going to be extra credit on the final exam. Part A will be 6.1, and Part B will be either of these two sections. So if you decide to study further, sections 6.2 and 6.3, here are the problems that will help you out getting that under your belt. It would be rewarding on the final exam for the sake of extra credit. So let's take a look into how this goes. This is the so-called method of cylindrical shells, but maybe even before getting too far on this, let me put that reminder down below of when to use which method. Okay, so here's our idea. The reading in section 6.3 starts off with a decent amount of geometry, finding volumes of cylindrical shells. Not too different than, say, finding the areas of washers like we were doing last couple examples. If you have a cylindrical shell, we mean something that's a cylinder, but it's just a shell. We want to know what is the volume of this entire thing. Imagine just a washer, but now a whole bunch of stacked washers going up. And that's a decent way to visualize this. The work in the textbook, the reading shows you that you can let delta R just be R2 minus R1. That's going to be the thickness of the shell. And then the volume can be re-expressed in this way. It's going to be 2 pi R times a height times delta R, where that's the thickness of the shell. So a good amount of algebra takes us here. I'll leave it to the reading to show how that comes together. It's a decent review on algebra to see all those parts track through. But notice what this really is boiling down to. If it's circumference right here, that means you're multiplying by 2 pi r. And the big question you might have is, what is r of x? If you can get the r of x, that's solving a good part of the problem already. Actually, I'm kind of debating myself on the colors. Let's go with green on that one. Next thing that you might want to have to get the volume of the cylindrical shell is the height. And the problems we'll look into, the height is going to be h of x. And that's the next natural question we want to ask to solve this. What is the height as x varies, the h of x function? And then the thickness, delta r, is the final component putting this all together. It's like catch up with the color coding. There we go. So this is the generic geometry that gets us started. Here's the actual problem that we'll be solving in these notes here. We take a curve, much like we were doing before, a curve that's going to bound a region from, say, A to B. We'll have vertical lines, x equals B, x equals A, horizontal line, y equals 0. And now we have this indefinite enclosed region in the xy axis. So all we want is a continuous function f from A to B. And then the drama in this problem is, imagine we're rotating this about the y-axis. That's inconvenient sometimes because our method for the cross-sections wants a rotation about the x-axis to work better. We know we can change the roles of x's and y's. If y equals f of x, that effectively means solve for x in this formula, and that's not always a tractable problem. Sometimes that is an enormously more difficult problem than finding the volume. Whenever that happens, we're going to use the cylindrical shells method instead, and so that's what the rest of the notes are all about. So just like before, imagine the region, and your imagination is a big part of this. Imagine this is rotate about this time the y-axis. Here's some amazing shading to show you what you would get if you did that rotation. Looks like a weird hat with a hole in the middle. It's a interesting volume that we'd want to find the volume for. I guess it's not a hat, it's not hollowed out, it just has a hole in the middle. To get this volume, we can just say partition the interval from A to B, equal widths, delta x, and then you would have these things. Here's the picture with n equals phi. Every one of these rectangles, they're going to rotate around, and then you would get n different cylindrical shells. Here, all the shells kind of stacked together. Formula above tells us how to get the volume of every one of those cylindrical shells. We would just take, say, the circumference. That'd be 2 pi times, we're using a midpoint on this one, x bar 1. We would multiply it then by a height. The height is going to be a function of x, so that's the f of x portion right there. That's height at x. So adapting the cylindrical shell formula, we actually have a height here for every one of these 5 shells all stacked together. And then we multiply by the thickness, delta x, in every single one of them. The delta x is just the difference of the radii, inner radius minus outer radius, or not delta x, but rather delta r. Putting that all together, whether you call it delta x above or delta r, the delta x turns into this. It becomes a Riemann sum, and that means you can rewrite the whole thing as a definite integral. It'd be an integral from A to B of 2 pi x f of x dx. So that entire 2 pi x just converts here. That's where the circumference came from. To get that, we just want to know what is the radius. Oh, sorry, Microsoft is really kind of pissed off today. Let me fix that. The radius is just x on every single one of these. And that's just going from here to here, the radius itself. F of x is the height of every single one of those. So that's where the f of x came from. And the limit of Riemann sums, when we go from a delta x, we just change that into a dx. So that's our new integral to solve, 2 pi x f of x dx. And stating it all as a formula, that's what we get as a limit of Riemann sums. And this is just a handy reminder. Sometimes these problems are just better thought in these terms. Whether you write out in this formula or the one that we sketched by hand above, it really just boils down to the radius of whatever cylindrical shell you're looking into, r of x, at a point, multiplied by the height of the shell, which is likely to be the function f of x itself. And you notice, let me see here, I think I have these colors backwards. Is that too late to fix? I think we can fix that here. That would just be too jarring to look at. I should have looked ahead to get those colors just right. This right here is going to be the radius function. And the problems that we'll look at in these notes, the radius is going to be just x, but it could really, in principle, be anything to match the problem. The height is just going to be the function. So there's the fixed color coding. Sorry for that switch. That's tough to track when the color coding switches like that. Put those two together, and that's the whole problem that we have to work out. So that's our new method. Well suited for whenever we're rotating something about the y-axis. So it's all about going in this direction. Now we'll put this to use, but any questions so far? Looking through just the short tour through the derivation. Okay, well, I think for what makes sense for the amount of time we have, we'll take a look into one more problem, take questions, and when we come back on our next class, we'll end a little bit earlier today. We'll be working through this document right here, the review problems down below, just fully reviewing for the course. So here's our last problem we'll solve for the day. We have a region bounded by the curve, y equals the square root of x to start. And for using y equals square root of x, it starts at 0. We're going to end at x equals 4. So that gives us a natural stopping point here for this vertical line segment. It's also bounded by the y-axis. And so we have this region here in blue. The whole thing is rotating this way about the y-axis. I think once again, these are pretty rough to draw, not always so easy. But the major things that we focus on when imagining what this would look like, again, another weird fruit bowl where there's one point at the very bottom. If you printed this, it's probably actually has a bona fide hole altogether, depending on how it might glitch out trying to handle a point. But we focus on this band right here, that rotating around. When that rotates around, we get this cylindrical shell. And if we can put it all together, knowing the radius going this way, the height going this way, the whole thing just boils down to that right here as a formula. So let me see if I can reformat this just a touch. So we can see it all on one page. That should do the job. So there's our formula above. And for these kind of curves, here's what the analysis would look like. We pick an x value on the domain of integration, integrating on the x-axis, so it'll go from 0 to 4. That's where the bounded region is relevant. So that means the radius of x is just going to be x. Same as this x we see here. So that's the radius, r of x going this way. When that rotates all around, it also has a height. The height, h of x. And this problem is just going to be square root of x altogether. So that's going this way. H of x will then give us a height from here to here. So with the radius, or if you're looking into this diagram, and a height given, we put that all together and we can say that the volume of this weird shape, as we integrate from 0 to 4, 0 to 4 comes from the bounds on x in the problem. is just going to be 2 pi times whatever the radius comes out as. Radius is x in this problem, multiplied by the height, h of x. In our problem, the height of a general cylindrical shell is square root of x. Let me fix that, highlighting a little bit better there. And then just dx. And really, that's the whole problem right to this point. Integrate 2 pi x root x dx, and then we're on our way. So at this stage, we can rewrite this as volume equals, let's pull out the constants, 2 pi. X root x, we can put in a better format for the purpose of integration. X root x is better expressed as x times x power halves, so x power 2 halves times x power a half, for x power 3 halves. So take 2 pi times the integral from 0 to 4 of the x to the power 3 halves dx. So that's our integral to solve for. And really now at this stage, it's just a section 5.3 problem using the fundamental theorem of calculus. On the next line, we can say that this is 2 pi times, put down x, add 2 over 2 to that, and we have power 5 halves. So multiply by 2/5. I'll leave all the constants just factored out to the left, just to save some time. And we're just going to integrate by evaluating this function from 0 to 4. So let's start by writing this as 4 pi divided by 5. Plug 4 in there, it's now 4 to the power 5 halves. Plug 0 inside, and it's just a minus 0. So a little bit more work with the exponents. 4 to the power 5 halves is just square root of 4 to the power 5. That means it's 2 to the power 5 really, for a value of 32. So now this is 4 pi over 5 times 32. And we're essentially done at this stage. This would be 128 pi divided by 5 units cubed. Or you don't have to say units cubed, just reminding us that once we get here at the end, that's still just a volume. And although I don't have a sketch for this shape, we can imagine what this would look like. Just some weird kind of bowl with a gentle slide going down below. If you need to manufacture those kinds of things, that's how much volume it's going to require for each unit. Well, we did it, folks. If you rotate something about the y-axis, does not have to be as painful as it was in the last problem, section 6.2. If you have a function of x, then this is the better method to go for. And the rest of the notes is just practicing these just a few more times. Same for the suggested exercises. But since we don't have enough time to fully go through this section, this is not an official homework exercise. 6.3 will just be suggested exercises if you decide to practice a few more and go for the extra credit question on the final exam. So that means this will be our last official problem for the day. Really the last official problem before we turn over to reviewing for the course. And I think we'll end a little bit earlier today, since it might be better, make more sense to start a review tomorrow, starting out a little bit more fresh as we tackle reviewing the entire course over the course of 2 days. But any last questions or comments at all then before we call it a night today? Okay, well, have a great night. At this point, we've completed all of the coursework for Calculus 1, so congratulations on getting through it. And we'll just be turning over to reviewing next class. I'll be mainly pulling problems from that document, but if you have any particular questions on any homework assignment, on any exam 1 through 3, and so on, don't hesitate to ask. Your questions are always better. If it's a student-directed review, that would be a better review. And if I run out of questions, this is the document that I'm going to be solving problem by problem for the class. But have a great night. We'll be back to it on Tuesday.